All right, Chapter 9, IPsec. So in Chapter 9, we're going to talk about the IP security framework. IPsec is not a protocol. It is a framework of protocols that allows us to provide things like confidentiality, message integrity, authentication, non-repudiation, and other things as well. All right, there's a whole bunch of individual protocols that go into making IPsec what it is. So we're going to focus on this chapter about looking at some of those concepts. In the next chapter, we'll actually look at VPNs, and we'll even take a look at how we could set up a site-to-site VPN utilizing the command line in a Cisco device, and then I'll also demonstrate some of the options that we have in the ASA. Even though it's not in the book, we'll take a look at what that looks like in the ASA using the VPN connection wizard, and take a look at some of the different settings, some of the different configurations that we have as options for setting up a VPN on the ASA, and look at the corresponding command line configuration that results from that. Cryptographic VPNs allow us to establish essentially private, virtually private, hence the term, connections from external networks into our corporate network or main site. Different types of VPNs exist, obviously. You guys are probably aware of this. Site-to-site VPNs. A site-to-site VPN, which is traditionally going to be IPsec, allows us to establish kind of a permanent virtual private network between two physical locations over some public domain. Traditionally, it's been IPsec, but what are some of the more kind of modern techniques that we can use to establish these site-to-site VPNs? Have you guys heard of DMVPN, Dynamic Multipoint VPN, Get VPN, Flex VPN? So there's many different options that we have to establish these site-to-site remote access VPNs. And then we have client-based remote access VPNs. And then we also have clientless remote access VPNs when we talk about teleworkers and mobile workers trying to connect to our location. So that's a discussion of IPsec versus the secure socket layer, utilizing SSL or TLS to create temporary VPN connections from a small office or home office, a mobile worker, a teleworker, and so on. So that's what we're going to look at in this chapter. Of course, we're going to look at the framework that's necessary in order to provide these functions, these virtual private network functions in the network today. So one of the principal considerations whenever we're implementing a VPN is to provide for confidentiality. This is done through encryption, right? And when it comes to VPNs, we typically will utilize some sort of bulk encryption algorithm, some sort of symmetric encryption like AES, to provide that confidentiality. Data integrity, which ensures that the data that was sent is the data that arrives at the destination without being modified or otherwise changed. So data integrity ensures that the data gets unchanged before it gets to the destination or as it gets to the destination. And we use hashing algorithms to provide this type of service. We use a hash-based message, what we call message authentication, or generating a message authentication code, which provides us the ability to identify whether or not data has been modified. Origin authentication. Well, what we would typically call non-repudiation of origin. Well, authentication is not necessarily non-repudiation of origin, but because we're providing origin authentication, we actually do achieve non-repudiation of origin as well. The connection is made with a desired communication partner. In other words, I don't want to establish a VPN with an untrusted entity, so there has to be some way for us to identify the entity that we're connecting to. And this is going to be either through some sort of pre-shared key method, or it's going to be through some sort of RSA or DSA key exchange method using IKE, the Internet Key Exchange, process to authenticate users and devices so that we can establish the session between the two endpoints. Then we have something called anti-replay protection. IPsec typically has some sort of function built into it that provides us a way of identifying whether or not a packet has been duplicated. We do this with different sequencing numbers and different transactional IDs that allow us to identify whether or not a piece of data has been copied on its way to its destination. There's not necessarily a particular protocol, or specific protocol tied to this feature. All of the other cryptographic features that we implement provide this service. And then finally, we have some sort of key management process. We have to have a way of initially exchanging our keys, our shared secret key that's going to be used for bulk encryption. That's typically done with some sort of Diffie-Hellman Key Exchange process. And then, post Diffie-Hellman Key Exchange process, we have to rekey based on the lifetime of the keys that we specified. And typically, the lifetime of the key can either be specified as a data lifetime or it can be specified as a time lifetime. In other words, the key is going to expire after X amount of minutes or X amount of hours or X amount of data. So these are the principles of what the IPsec protocol suite provides. We will be talking about all of the algorithms and all the protocols that are built into this framework that provide us the ability to provide these services to the enterprise. As far as confidentiality goes, we're going to use a bulk encryption algorithm. These are the four most common: DES, triple DES, AES, and SEAL. We already talked a little bit about DES being a 56-bit, well, technically a 64-bit encryption algorithm, but because we don't use all the bits, it's about a 56-bit encryption algorithm. Triple DES, which is 3 times DES, can either provide 168-bit encryption or 192-bit encryption, depending on whether or not you're using a 2-key process or a 3-key process. And then, of course, the advanced encryption standard, which comes in many, many variants, and that is the predominant standard today. AES, being that it provides either a 128-bit key or 256-bit key space or a 512-bit key space. So it's a much more robust algorithm. One of the things that's absolutely critical in order for us to establish a shared secret key is there has to be a way for us to be able to exchange those keys over a public domain. It's kind of a little bit of a conundrum, right? We want to establish a secret channel over public domain, but in order for that channel to be secret, we have to have a common key so that we can do our encryption. But how do we exchange a common key if we can't send the key over this clear channel? If I send the key over the clear channel, then it's not going to, the key could get compromised. Somebody could see that exchange, they could copy the key, and then they would have access to our secure data. So we have to have a way of providing that exchange method. And the key exchange process is typically the Diffie-Hellman Key Exchange process. That's what DH represents. Or the elliptical curve if we're using kind of a more modern technique, what we call the next generation of cryptography. Elliptical curve Diffie-Hellman is a way for us to provide that service as well. All right. Let me pull something up. So the Diffie-Hellman Key Exchange process, kind of in a layman's terms, kind of a visual way of representing the process looks a little bit like this. So Bob and Alice want to be able to exchange data securely, but both Bob and Alice don't know what shared secret key to use. There has to be a way for them to establish a shared secret key without actually sharing the key over insecure channels. So Bob and Alice have a common paint. This is a mathematical value that they both generate. We don't have to get into the modular math and all of the different mod P and G components and everything else that goes into the calculation. But let's just assume that Bob and Alice have a common paint. All right. not only do they have a common paint, both Bob and Alice generate or have a secret color that they don't share with anybody. All right? That secret color is only known to Alice, orange, and the teal one there is only known to Bob, and that's never shared. So what Alice does is she mixes her secret paint with the common paint. Bob mixes his secret paint with the common paint, and then they exchange that mixed paint with each other. So if somebody intercepts that mixed paint, it's practically impossible for them. Well, it is impossible for any, well, what we usually call the person in the middle is Evil Eve. That's what they usually use. So let's say Evil Eve gets a copy of those that public transport paint that we see there. There's no way that Evil Eve can unmix that paint, right? If I took a couple of different paint colors and mixed them together and then gave you that paint and said, okay, unmix this back to its original two colors, it'd be practically impossible. I mean, it would be impossible. But, all right. So because Bob's color here, this kind of light blue one, includes his private paint and the public paint, if Alice mixes that with her private paint, and if Bob mixes his private paint with Alice's public transport paint, they're going to end up with the same color because they're mixing the same three colors together. Does that make sense? And that becomes your common shared secret key. That becomes your shared secret key. So we're never exchanging anything that's private over this public transport. And what they say there is assume that the mixture separation is expensive. What do they mean by that? Make sure that the mixture, what do they say? The mixture separation is expensive.
I mean, it's technically possible, just unlikely.
Yeah. It means that it is possible. There is the potential of unmixing those paint colors, but it's not very practical. It's computationally expensive. It's going to take a lot of time. It's going to take a very large work factor. That's what we define in terms of the paint. It's just a very high level of a work factor, meaning that it's not very practical. And in essence, it's not something that would be accomplished in a relatively short amount of time. So that is a very, very generic way of looking at the Diffie-Hellman Key Exchange process. There's obviously math involved in this case, specifically modular math, and where we have variables that go into each formula, and those variables represent the common paint, the private paint, and the mixed paint, and so on. But that's really the extent of what we need to know with regard to the Diffie-Hellman Key Exchange process. All right, now that we have a shared secret key, we can then start encrypting our data. In addition to doing our confidentiality with our encryption protocol, we also want to make sure that we are implementing some sort of message integrity. But in order to have message integrity, true message integrity, we can't just use a hashing algorithm. We have to insert some sort of secret sauce into the hashing process. This would be a secret sauce that only the parties involved would know, some sort of secret key. That means that the full-length authentication hash is going to be unique, and even if somebody is able to decrypt the data, they can't modify the data because they don't know the secondary secret key that's used for the hashing. A couple of different hashing algorithms that exist. Actually, there's more than two, but did I miss that? Nope. There's more than two. Well, there's two primary variants, right? MD5 and SHA, the message digest hashing algorithm and secure hashing algorithm. But within the SHA realm, there are several different versions of SHA that we can run. Another component is authentication, being able to authenticate the peers to ensure that the peer that I'm communicating with is the appropriate device that I want to communicate with. Pretty typically, it's going to be some sort of pre-shared key. That's not uncommon, although I doubt you guys actually probably use pre-shared keys for your VPNs. but you can also use the public key infrastructure, RSA signatures or elliptical curve digital signature algorithm. So this is really the most advanced and most modern method of doing up-here authentication, elliptical curve digital signature algorithm. But we could use RSA signatures, or we can use RSA encrypted nonces. What is a nonce, by the way? Any idea? It is any kind of cryptographic variable or cryptographic digest or data that we use only one time. Right? Nonce means that basically n is the variable and once is using it one time. So a nonce is something that we only use one time for the authentication or whatever it might be. So this is the entire deal. This is the framework, IPsec framework. Like I said, it's not really just a protocol, although we do identify IPsec as a protocol in the form of ESP, which is the Encapsulated Security Payload, or AH, which is Authentication Header. ESP provides encryption. You'll notice that AH, well, it's actually kind of not drawn well here. AH would not include encryption, so we're not looking down these columns to see what's being provided here. This is kind of just a separate row, but this is encryption, this is authentication, this is both. Okay? ESP is Encapsulated Security Payload. That means that we're actually encapsulating the data either in tunnel mode or transport mode, and it has some form of encryption. Although we can run tunnel mode and transport mode with just authentication. And the confidentiality components that we have are DES, triple DES, and AES. Data integrity, MD5, SHA-1, SHA-2, data origin or origin authentication, pre-shared key, RSA, elliptical curve digital signature algorithm, and then finally key management using a key exchange process, Diffie-Hellman, elliptical curve Diffie-Hellman, Internet Key Exchange, and Internet Key Exchange version 2. So by putting all of these blocks together, we can actually build out this secure architecture, this way for us to communicate over a public domain. And so you have to really kind of drill down and take a look at all of these different options. So what is the Internet Key Exchange? IKE is a protocol that automates the key exchange process. The first thing that has to happen is, and we're going to see a configuration later on where we actually look at the parameters that are established in the IKE proposal, but the first thing that has to happen is we have to have some sort of security association parameter negotiation. Don't say that 10 times fast, right? Security association parameter negotiation, meaning that we're establishing all of the parameters of establishing a secure channel. You know, what Diffie-Hellman algorithm are we going to use? Are we going to use perfect forward secrecy? What is the lifetime of our keys going to be? Is it going to be based on data? Is it going to be based on time? What is the encryption algorithm that we're going to use? What is the hashing algorithm that we're going to use, and so on? How are we going to authenticate one another? So these are all the SA parameters. There's a key generation process, there's a peer authentication process, and then there's a key regeneration process that's part of this as well. Most people, when they think of IKE, particularly from the perspective of a site-to-site IPsec VPN, they think of this as kind of a phase one type of deal. Phase one is where we're kind of just establishing the parameters of our encrypted channel or our secret channel. Okay? IKE v2 was created to overcome some of the limitations of IKE v1. Much simpler protocol, much faster protocol. Fewer exchanges take place to establish the bidirectional security associations. NAT traversal is allowed. NAT traversal means that we can establish these associations through different NAT boundaries. Dead peer detection to identify when a peer is no longer responsive, and so on. Stronger security, denial of service protection mechanisms, other functions built into Ike v2 that provide additional security. Much more reliable. We use sequence numbers, acknowledgments, and error correction mechanisms in Ike v2. Much more flexible, so we have the integration of what we call EAP, the Extensible Authentication Protocol, and mobility with MobiIke, Mobile Ike for layer 3 roaming, meaning that we can maintain security associations even if you move from one layer 3 domain to another layer 3 domain. So lots of functionality there, and we don't necessarily get into the specifics of it. We are going to focus primarily on the configuration and verification and troubleshooting, but let's take a look at the different phases. So router A, and we'll see the configuration of this a little bit later on actually, but router A wants to establish a secure tunnel to router B, okay? So the first thing that happens is we send our policies. So router A has a list of Ike policies on it. Router B has a list of Ike policies on it. And only one policy is going to be used, but the routers have to negotiate which policy that's going to be. All right? Now let's say that A is initiating the process. A is deciding, I want to set up the VPN because the interesting traffic, host A pinged host B, so the interesting traffic is flowing from the left to the right. What router A is going to do is it's going to send all of the proposals that it has, Ike proposals, to router B. And it might be 3 or 4 or 5, maybe there's only one. It just depends on how you configure router A. But all of those Ike proposals are going to go over to router B. Router B is going to do a comparison between the Ike proposals it receives from router A and the proposals that it has configured on its own router. And it's going to make a decision on which proposal to use, and it will tell router A, I want to use proposal XYZ. Okay? So now we've established the parameters of this exchange. We've decided that we're going to use this encryption, this hashing algorithm, these lifetimes, these data, rekeying lifetimes, etc. The next step that happens is the Diffie-Hellman Key Exchange, where we are obviously sharing secret keying material using that paint bucket approach. Obviously not paint, but you get the idea. So that we can establish some sort of shared secret key. And then, believe it or not, you would think that this would almost happen beforehand, but the peers actually authenticate each other in a secret session. I mean, it makes sense. We don't want people on the internet or people in the public domain to capture the identity of the peers that are actually communicating with one another. So we authenticate our peers in some sort of private security association. This is not a VPN tunnel per se. I mean, it's not our bulk encryption tunnel. It is our initial encryption tunnel that allows us to identify and verify our peers in a private way. All right? So router A is going to verify router B. Router B is going to verify router A. And that could involve just making sure that we both have the same pre-shared key, or you could use RSA here, or DC or ECDSA. So here's that phase 1. So router A has a bunch of different Ike proposals built into it, policy 10 and policy 20. The number of the policy actually does make a difference. The lower the number, generally the more preferred the policy, but it's not really router A's choice. What router A is going to do is router A is going to send all of its policies over to router B. Router B is going to compare those policies against the policies that it has configured, and it's going to match up a policy. So in this case, policy 10 on the left matched up with policy 200 on the right. We're going to use AES for encryption. We're going to use SHA-256 for for our hashing algorithm. We're going to use pre-shared keys for our peer-to-peer authentication. We're going to use Diffie-Hellman group 5 for our key exchange and key management process. And we're going to have a lifetime of 86,400 seconds for the keying material. So after 86,400 seconds, we're going to rekey, and every time that time expires. Now, you'll notice that the time doesn't necessarily match here. So we're going to negotiate down to the lowest timer value, 43,200 seconds. The rekeying actually will take place in this particular case. So router A sends all these proposals over to B. Router B picks a proposal and lets router A know we're going to use this proposal. Do you have to have multiple proposals? No. If you're establishing a site-to-site VPN and you own both of the devices and you control the configuration on both of the devices, you're not required to have multiple proposals. It's just oftentimes you're establishing VPN sessions with multiple entities, and one organization or one group might decide to use a certain set of variables in their proposal, whereas somebody else might use a different set. So you have to have multiple proposals to facilitate those different communications. Okay. Oh, there's that pretty diagram. I thought I had added this in here. So now we're going into the Diffie-Hellman Key Exchange process. I'm basically breaking down this part of it right here. Right? So we just looked in this slide, we just looked at the first block right here, policy exchange. And now we're going to be looking at the Diffie-Hellman Key Exchange. And at least this particular slide here, I actually pulled this from my CISSP class, but this particular slide, it does describe the paint bucket scenario. But it also gives you all the variables and the math that's involved in actually processing this data. It's more for your information. You're not going to need to know this for the exam, but you can see that the common paint is actually a variable that they both agree on. G and P, which is primitive root. G is a primitive root of P, and these are the values that they agree on. So they both agreed on G is 7, P is 11. It goes into the formula. I'm not going to go through the specifics here, but I decided to throw this in here just so you can see the math that's actually involved in making this work. It's very simple math. I mean, it's not, well, it's easy to calculate. It's very difficult to reverse, but so it is computationally expensive to reverse. But as far as the actual physical calculations go, it's not that complex. We're using modular math. I'm not going to get into how modular math works, but it's kind of 5th grade math, basically, maybe 6th grade math. But in the end, the goal here is to be able to establish a shared secret key, or what we call a common paint. And that's what we end up with in the end. Okay? And by the way, this is this common paint is what we're going to use as our shared secret key for our bulk encryption. All right? The third exchange is to authenticate the peer. All right? This is done under the protection of a security association, meaning that this particular part of the process is encrypted. Anybody that's Evil Eve is over there sniffing our data, she's not going to be able to identify the identity of our peers because these transactions are hidden. Several different methods of authenticating your peers. You can use a pre-shared key. You can use RSA digital signatures. You can use encrypted nonces and elliptical curve digital signatures. All right? Two things that can happen here. Either I'm going to authenticate my peer, and then I'll continue to move on to the next phase, which is phase 2, the encryption phase of our process. Or I will fail. The peers will not authenticate, and we will terminate the process. Okay, ISA-KMP. This is a term that you'll see, maybe not on the test, but certainly we'll see in any time you're dealing with a Cisco VPN. ISA-KMP stands for Internet Security Association Key Management Protocol. Okay.
The port that it runs over.
Oh, yeah.
We use ISACAM, non-ISACAM a lot.
Yes. Yeah. Well, essentially, when you see ISACAMP or ISA-KMP, that's going to relate to all of your phase 1 functions, right? In fact, if you want to verify whether the phase one is working, you do a show crypto ISA-KMP SA, right? Yes, sir. Okay, give me a sec. So once phase 1 is done, then we can move on to our phase 2 process, where there's still an additional set of negotiations that occur to identify the encryption algorithm that we're going to use and all the parameters of our security associations for phase 2. All right? And we'll see what that process looks like a little bit later on. When it comes to phase 2, there are a couple of options that we have. We can do authentication, or we can do encryption, or we can do both. Authentication, AH, is IP protocol 51. As you can imagine, it is going to provide some sort of authentication function, what we call origin authentication. It's going to provide some sort of data integrity with a hashing process, anti-replay protection, but does not provide any type of confidentiality. Very, well, we don't usually, you just usually will not see this in VPNs today. Obviously, if you're going to go all of these different steps to provide, those aspects, you're going to obviously put in some encryption as well. So that is something that we have to do. But AH is an option with IPsec where you can just run authentication without encryption. ESP, the Encapsulated Security Payload, which runs over protocol 50, meaning that there's no TCP or UDP function in this. It is literally an IP-based protocol, like ICMP or EIGRP or OSPF. It's going to provide everything that AH provides, but it also provides confidentiality in the form of encryption. So if I'm just running AH, I transport my data. I have my AH header, which includes some sort of hash, based on the IP header data, the data field itself, my payload, and a key, and I simply drop that into the AH header. I send that information along the way to the destination. Both sides have a common key that they use, so they can both verify the hash, which then provides authentication. Right? We're not providing authentication necessarily in the form of, hey, you have a password, or excuse me, you give me your username and password, I'll give you my username and password. That's not what we're talking about in this particular case. Okay? We're simply talking about the ability to authenticate the peers based on the fact that they have some sort of shared secret key. But the data is still sent in plain text. That's my payload. That payload is not encrypted as it goes over the internet. ESP, on the other hand, depending on the version of you run, whether you run tunnel mode or transport mode, will define how the header is created. In this particular case, we're looking at tunnel mode. But the key difference here is that we've got our ESP header, which provides all of the encapsulated security payload data, but all of the payload is encrypted. The data is encrypted, the IP header is encrypted, the original IP header is encrypted. So we have a transport header, which is our outer header, which allows us to transport the data over public domain, and then we have the internal data. So if you look at the process here, you've got some sort of private network here, some sort of private network here. And the routers understand those private networks and reachability for those private networks. You've got a public interface here, you've got a public interface here, and there has to be some way to route between those interfaces over the internet. Well, that routing function is done with this header right here. That outer header is what allows us to route the traffic over the public domain. The inner header, which is encrypted, is what allows us to route the packets within the enterprise. So you can imagine the process here. I've got my unencrypted data going to the router using my standard routing protocols, my standard routing principles, default gateway, routing, whatever it might be. I've got some sort of VPN configuration on this external interface, either with a crypto map or some other method. And when the data matches using an interesting traffic ACL, that crypto interface, that's when the encryption occurs, and that's when we create this new payload. All right? So there are two ways that we can transport data using ESP. Or AH, by the way. This would work with AH as well, but tunnel mode and transport mode. As you can see, tunnel mode is what we were just describing on the previous slide. You maintain the integrity, and the inside IP header is encrypted, and then you've got your new, essentially your transport header, which allows us to route over the public domain. Is created on the outside. What is important about this concept? I mean, obviously, the important piece is that your data is encrypted and the original IP header is encrypted. But what else is important about this concept? Overhead. There's overhead. You've got your ESP overhead, you've got your IP header overhead. So you need to make sure that you take that into account, especially when you're dealing with packets that might exceed a particular MTU. You need to identify how that overhead is going to be handled. So typically, we're reducing the MTU size of our data field to account for this additional overhead. All right. So I've gone through phase one, the 3 steps of phase one, proposal exchange, Diffie-Hellman Key Exchange, and then peer authentication. And now I'm moving on to phase 2. So there's more than 3 steps here, but phase 1 did include the proposal exchange, Diffie-Hellman Key Exchange, and the peer authentication. So 3 general steps in phase 1. Now we're going into phase 2, and you can see that we're establishing or negotiating all of our IPsec parameters. What encryption algorithm are we going to use? What's the rekeying time? How are we going to do our rekeying? Are we going to use, perfect forward secrecy? Well, that's kind of more established in the phase 1 process, but it does have to do with how the rekeying takes place between our exchanges. Are we going to? So perfect forward secrecy allows us to establish how long a key is going to be valid for. And if you enable perfect forward secrecy, that means that you're changing the keys on a regular basis. So essentially every exchange that takes place, you're going to have new keying material for each of those exchanges. It's not typically used for site-to-site VPNs. It's more used for remote access, but some people do like to use it to establish a site-to-site VPN. Just provides an additional layer of security, but it also provides an additional amount of overhead. All right? The other thing I want to point out here is that these security associations are not full duplex. They're simplex security associations, meaning that we're establishing an SA in each direction. In fact, depending on how many subnets and how many networks you're passing over this VPN tunnel, you might actually establish even more than just 2 security associations. I've seen tunnels that have 4 or 6 or 8 different security associations tied to it, based on what we're passing over that tunnel. All right? So let's take a look at, from end to end, what this configuration looks like, and we'll see if we can't establish this VPN between these 2 devices. All right? So actually, we're going to see this implementation in the next lesson. So if you're watching this video, go on to the next lesson. But essentially, that's what we're going to do. We're going to establish a VPN between 2 routers over some sort of internet. In our case, we'll simulate that internet connection. that's going to allow client A to be able to talk to client B over this public domain. So we need to be able to identify what data to protect. We do that with something called a crypto ACL, which is an access list or an interesting traffic ACL. It's an access list that allows us to identify what traffic is going to be encrypted as opposed to what traffic isn't going to be encrypted. We don't want to encrypt all of our internet-based traffic. We only want to encrypt the traffic going from the network for host A to the network for host B. How is the data going to be protected? What type of encryption are we going to use? And where do we send that protected data? So we need to identify our peers. All right? We will take a look at that, like I said, in the next chapter. We'll take a look at that configuration. There is this Suite B series of protocols. The US government recommended these different cryptographic algorithms, part of the FIPS 140 standard by NSA. Basically what they defined is you should be utilizing these cryptographic protocols to establish your tunnels or your private networks, your virtually private networks, to ensure that you have the latest and most secure security algorithms in place. So for confidentiality, don't use anything less than AES. For integrity, SHA-2. The key space in that would depend on what you're trying to accomplish, but at least use SHA-2. Use the elliptical curve digital signature algorithm for peer authentication, and use the elliptical curve Diffie-Hellman Key Exchange process for key management. What we call the Suite B of protocols. Suite B cryptographic suites for IPsec, I should say. This is all approved for secret and top secret data for classification, so when you're transporting this type of data, this is what you would want to use. All right, we already talked about some of the benefits of running IKEv2. You know, it adds additional security, it's much more efficient, et cetera, et cetera. We have flexible authentication options and so on, but it's also a much faster process. Notice that we only have really 3 things that get exchanged in this exchange process. So it's going to provide us enhancements to what we're doing with IKEv1. The overall purpose of the protocol and the function of the protocol is the same. We just have some additional features: dead peer detection, NAT traversal, fewer exchanges during the IKE process, flexible peer matching, and so on. When you get into the CCNP security, you get into a lot more detail and as to what the difference of the protocol is versus other protocols that might exist, or IKEv1, I should say, in this case. All right. So that concludes the cryptography chapter. What we're going to do is we're going to look at an example in the next lesson. We'll take a look at an example of configuring a VPN tunnel between 2 routers. I'll pull up GNS3 and we'll go through an example and take a look at that configuration and look at some of the different troubleshooting techniques that we can use to verify the operation of the tunnel and so on. So we'll see you guys in the next lesson.